Subscribers, welcome back to another episode of Science with Surbeck. Today what we're going to talk about is section 15.1, which deals with the introduction to solutions. Now before we get going into these notes, there are a few objectives I would like to outline. Objective number 1, describe the characteristics of solutions and identify the various types. Objective number 2, relate the intermolecular forces in the process of solvation. And objective number 3, define solubility and identify factors affecting it. So we start out here with just a basic definition of what our solutions are. And solutions are just defined as a homogeneous mixture containing two or more substances. Now, when we talk about solutions, we need to talk about their parts, and there's two major parts to solutions. The first part of a solution is known as the solute. And a solute is defined as the substance that is dissolved. The other part of a solution is the solvent. Now, the solvent is the substance that is dissolving, or we call this the dissolving substance. Now, it's important to note that the solute and the solvent of a solution are impossible to distinguish from one another. Now, it's important to note that solutions can exist in any of those three states of matter. So let's go ahead and let's identify some examples of each of those states of matter. And so we'll start out with solids. So an example of a solid solution is something called nitinol, which is the metal they use in braces. Now the solute in nitinol is titanium. And the solvent in nitinol is nickel. Now solutions can also exist in the gaseous state. An example of this would be the air in Earth's atmosphere. The solute in air of Earth's atmosphere would be oxygen. And the solvent would be the nitrogen. Now, solutions can also exist as liquids, and this is the most common form of solutions. And since this is the most common type of solution, there's lots of examples. One example would be an aqueous solution like salt water, what you'd find in the ocean. Now, another important note here is that solutes and solvents of different states of matter can combine together to form a single solution. A great example of this happening is carbonated beverages. The solute in a carbonated beverage like a soda is the carbon dioxide, which is in the gaseous form. The solvent in carbonated beverages is the water, which is in the liquid form. Now, another thing that we need to identify here with solutions is how solutions form, or in some cases, why two things when they're mixed may or may not form. So we start out here with that statement that I just said, and that is this: substances that are mixed may or may not form a solution. The solution formation is going to depend on a variety of factors. Now, to help identify these factors here, we need to go over some terms, the first of which is soluble. Now, something is soluble when a substance will dissolve in a particular solvent. Now, again, if a substance is soluble, it will form a solution. And a good example of this is sugar being dissolved in water, or how we state it here, sugar is soluble in water. Now, within this term of soluble, we can actually define another term which is known as miscible. Now, if something is miscible, this is a term that is used to describe when two liquids are soluble in each other in any proportion. And an example of two liquids that are miscible is antifreeze, which is a solution of water and ethylene glycol. Now, another term that we need to be familiar with in this topic is something known as insoluble. And so if something is insoluble, it's when one substance does not dissolve in a solvent. And if something is insoluble, then it will not form a solution. A good example of this is sand that is in water. No matter how hard you stir that sand and water mixture, it is not going to dissolve together, and therefore it's insoluble. Now, just like we did up top here, there's another term associated with insoluble, which is Miscible. And Miscible is a term used to describe two liquids that cannot be mixed together, but they separate shortly after they are left alone into those individual components. Again, Miscible says here it's a term used to describe two liquids that can be mixed but separate out shortly into their individual components. Now, a great example of this is an oil and water mixture. Now, again, I ran out of room here, but our example for immiscible liquids is oil and water. And you can mix those two together, but they're going to separate out very, very quickly after you stop mixing them. Now, what we also need to know is some more terminology here with solutions, and we start out with this term known as salvation. Salvation is defined as the process of surrounding solute particles with solvent particles to form a solution. Now, in the process of salvation, we need to know that there are attractive forces that exist between three different components or three distinct areas. The first of these attractive forces is the pure solvent particles. The second attractive forces is the pure solute particles. And the third attractive forces we need to be worried about here is the solute and solvent particles interacting among each other. Now, we could break these first and second attractive forces that we talked about into that term we know as intramolecular forces. And this third attractive forces can be classified as an intermolecular force. Now, knowing these basic information, we need to understand the steps that it takes for salvation to occur in a solid solute. Now, salvation of a solid solute, again, don't get caught up in the terms here, but think of making Kool-Aid. Kool-Aid has that packet, the flavoring packet, and some sugar, and that would be the solid solute. And then you'd add the water. So think again, making Kool-Aid could be the salvation process of a solid solute. So the first step here is the solid solute is placed in the solvent. And again, think about making Kool-Aid. The solid solute would be the Kool-Aid flavoring packet, and it would be placed in the solvent, which would be the water. Now, what happens here in step 2 is that the solute particles can completely surround the surface of that solid solute. So again, let's stick with that Kool-Aid example here. So for step 2 here, the solvent, which we said was the water in our Kool-Aid example, is surrounding that solid state or the Kool-Aid. Okay, so think about it like this. I'm going to use a real simple drawing here. If we have the Kool-Aid, and I just wrote out the name. What is happening in step 2 is that these water particles, which I'm going to draw in blue, are surrounding this solid particle here from that flavoring packet. Now, step 3 is really important, and it is really technical. And so what step 3 says is that if the attractive forces between the solvent and solute particles are greater than the attractive forces holding the solute particles together, the solvent particles pull the solute particles apart and surround them, just like this picture shows. So again, if we tie this whole page of notes together, this means here, number 3, the third step in solvation, is that the intramolecular forces were less than the intermolecular forces, and as a result, the solution forms, and we get a product or an end goal here of our solute, our solid state there, being surrounded by the solvent. Again, don't think too hard on this. Think of our Kool-Aid example. You have solid Kool-Aid, you pour some water in, the solid Kool-Aid flavoring packet is dissolved by the water, and we call this in chemistry the solvation process. Now, one thing that is really associated or closely tied with the solvation process is this term or this saying that likes dissolve likes. And so what likes dissolves likes means is this. Generally, what happens here, this is the general rule used to determine whether solvation will occur between a solute and a solvent. So now to utilize this term or this saying that likes dissolve likes, we have to know this. You must examine the following 2 things. One, the first thing that you must examine is the bonding and the polarity of the particles involved. And then 2, you must identify or you must examine the intermolecular forces between those particles. Now, to put all of this into perspective, let's take a look at a solution of salt water and how it's produced from start to finish. And so we start out here with aqueous solutions, which aqueous is going to mean dissolved in water, of ionic substances. So again, example here, we're going to use sodium chloride or salt in water. And again, aqueous, what that means is a substance is dissolved in water. And so what we have to remember with this is we have to remember some things about the water, which is a solvent, and the sodium chloride. The 2 things about water that we have to identify or know is as follows. Number 1, water molecules have dipoles with partially positive and partially negative ends. And the other thing with water molecules that we have to remember is that they're in constant motion as described by the kinetic molecular theory. Now, when salt, sodium chloride, is placed in water, we have to remember a few things, or some things are going to happen, and they are as follows. Number 1, water molecules collide with the surface of the crystals from the sodium chloride. And then number 2, the charged ends of water molecules attract the positive sodium ions and the negative chloride ions. So far, what we have up to this point of an aqueous solution, water, dissolving an ionic substance is this. We have separated out the ions. So let's say we have our Na+, and I'm going to draw over here the Cl-, and so we've separated out our ions, and now we've surrounded them with those water particles, okay? So the the ionic form of sodium, the Na+ here, is going to be attracted to the partial negative charge of that oxygen. And remember how we represent the partial? It looks like a weird S with a minus. is going to be attracted to that partial negative of that oxygen. And you could do the same thing and surround this entire particle. Now, what we also have here is the partial positive around the H. Just due to space, I'm not going to put it here, but the partial positive of that H would be closest or attracted to those negative chloride ions. So again, the partial sign here, this would be a partial positive of those H's. And again, you could draw several water molecules to surround that chloride ion and the sodium ion respectively. Now, each of these also have partial positive and partial negative charges. You could draw that on the oxygen here as well. I just saved some space here so we did not run into that issue. Now, we need to continue talking about this example of salt being dissolved in water, and we need to go one more step here. So we'll keep going, we'll keep moving through this same example here. And so our example here, our last point that we need to make with the example, is that the attraction between dipoles of a water molecule and the ions of the sodium chloride crystals are greater than the attractions among the ions of a sodium chloride crystal alone. So this statement here is going to result in the sodium chloride ions breaking away from the surface of that crystal. It also causes the water molecules to surround the ions, and solvation of the ions occurs when this process happens. Now, it should be noted that when we have those solvated ions, what happens is they are going to move into what we call the solution. Now, as this process continues, more ions are then surrounded or become surrounded by water molecules and eventually are solvated into solution. Now, this solvation of sodium chloride ions continues until the entire crystal has dissolved and all the ions are distributed throughout the solvent. Okay, so we wrote down a lot about just salt dissolving in water, but we need to think big picture, or every piece involved in this process. We have a lot of knowledge about the particular parts that make up some of these solids like sodium chloride, and we also have a lot of knowledge about the solvent as we had in water. We need to merge together, we need to think big picture. All of those little things that we've talked about are affecting if something can be dissolved or solvated or not into a solution. So when you form a solution, yes, it may seem like a simple process out front, but we need to think about everything that has occurred up to that point, or what we have already learned to identify this. Now, let's go over another example. This will be a lot shorter example, and this is going to be of gypsum in water. So we'll transition here, and we will go to our example of gypsum in water. So gypsum is composed of calcium ions and sulfate ions. Now, just for your information here, gypsum is used in plaster. Now, if we try to dissolve gypsum in water, we couldn't. And that's because gypsum is insoluble in water. Now, specifically, if we get in the details here of why gypsum is insoluble, we have this. The attractive forces in calcium sulfate are strong and cannot be overcome by the attractive forces exerted by the water molecules. Now, what this is saying, this detailed explanation here is saying, is that because of all of these things, salvation is not going to occur when gypsum is placed in water. Okay, so now on the flip side here, we need to talk about molecular compounds. So remember, ionic compounds are involving ions, but if we talk about solutions of molecular compounds, we need to focus on this. Molecular means that we have covalent bonded atoms, okay? So when we think about that, we need to think about covalently bonded atoms. And we start out here with an example of an aqueous solution that could be produced, and that is sucrose or sugar in water. So we need to look a little bit closer at sucrose. And sucrose molecules are going to have several OH bonds. Now, these OH bonds cause the molecule to be polar. And each of these OH bonds becomes a site at which hydrogen bonding with water can occur. Now, since we have a base knowledge about sucrose in terms of the polarity and the bonds that could occur, or hydrogen bonds that occur between sugar and water, we need to talk about when water and sugar are mixed together. So number one, water molecules are going to collide with the outer surface of the crystal from the sugar. And then the attractive forces among the sucrose molecules are overcome by the attractive forces between polar water molecules and polar sucrose molecules. So as a result here, the sugar molecules are going to leave the crystal and become salivated by the water molecules. Okay, so again, sugar dissolving in water occurs, and so salivation occurs, and you form that solution. Now, if you have a molecular compound trying to be dissolved in another molecular compound, sometimes you don't get that salivation to occur, which means you don't get the solution to happen. And so a great example of this is oil and water. And so what happens with oil and water is this. It is not going to form a solution with water, or oil does not form a solution with water, because there is little attraction between the polar water molecules and the nonpolar oil molecules. Now, for oil to form a solution, another nonpolar solvent is needed to dissolve the nonpolar oil. Okay, so another term that we need to go over is the rate of salivation. Okay, so just another term associated with our introduction to solutions. And the rate of salivation is going to involve this. The first point we need to know is that salivation only occurs when and where the solvent particles come in contact with each other. Now, just as a reminder, the salivation is going to occur when a solute and solvent particles collide with one another. Now, there's three key things here, what I just wrote down, and that is the solute, the solvent, and this collision or collide here. And so the more and more we can get the solvent and solute to collide, the faster and faster that particular solution is going to occur, and the faster we're going to get that salivation. So we're going to increase that salivation. So there's three ways to increase the collisions between solute and solvent particles, and they are as follows. The first way is agitating or stirring the mixture. And so what this does is it's going to dissolve solute particles away from the contact surfaces more quickly. And the other thing that it does is it allows for new collisions between solute and solvent particles to occur. Now, I ran out of space here to talk about the other two ways, so I'm going to grab another blank sheet of paper and talk about our second and third ways to increase those collisions between solute and solvent particles. So we get into our second way to increase the collisions, and that is increasing the surface area of the solute. And this is going to occur when the solute is broken into smaller pieces. Now, as you have greater surface area, this is going to allow for those more or increased collisions. Now, a great example of this way to increase your number of collisions is this, and this is just thinking logically here. If you have a teaspoon of granulated sugar, so that means it's busted up into small pieces, it's going to dissolve more quickly than if you have the same amount of sugar in a cube. Now, the third way you can increase those collisions is by increasing the temperature of the solvent. What this does is it increases the kinetic energy of the solvent particles. And as a result, it causes more collisions with the solute particles, and the collisions are going to have greater energy. Another good example of this third point here is when you have sugar, and that sugar is going to dissolve quicker in hot tea than it is in iced tea. All right, so let's continue moving on here with just our introduction of terms associated with solutions. And our next term that we need to discuss is that of the heat of solution. Now, heat of solution is defined as the overall energy change that occurs during solution formation. Now, we need to know this, that during solvation, the solute must separate into particles and move apart. And this process is going to require energy. Now, the heat of the solution can help explain why some solution formation does the following. Number one, releases energy as they form. And we know this as an exothermic formation here. And number two, we can have solutions that absorb energy as they form. And we know that as an endothermic process. Okay, so moving on here, we can talk about solubility, which again is another term associated with our solutions, but it's important to identify and know. Okay, so solubility is defined as the maximum amount of solute that will dissolve in a given amount of solvent at a specified temperature and pressure. Now, solubility is usually expressed in grams of solute per 100 grams of solvent. Again, grams solute per 100 grams of solvent. Now, a good example of solubility, or putting it into a little perspective here, is adding so much sugar to iced tea to all of a sudden the sugar crystals begin to accumulate at the bottom of the container. So at this point here, you've reached that max solubility, and that is because only a limited amount of solid or solute can dissolve in the tea. In this case, that solute is the sugar. Now, the amount of tea that can be dissolved is dependent upon the temperature and pressure. Now, let's take a little bit deeper look at solubility at the particle level. So, the first thing that we need to know is this. The solute is first added to the solvent. And when this happens, the solvent particles collide with the solute's surface particles. And what also happens is the solute particles begin to mix randomly among the solvent particles. The second thing that we need to look at here is that the solute particles are carried away from the crystal and are salivated. Now, the third thing that occurs is that the salivated particles increase to a point at which results in increasingly frequent collisions between salivated and solute particles and the remaining crystal. Now, some of these salivated particles are going to rejoin the solute crystal or that crystalline structure. Now, this particles or the salivated particles rejoining the solute crystal is a result of the same random mixing that causes the solute to be solvated. Now, the fourth thing to be aware of is that as solvation continues, the crystallization rate begins to increase and the solvation rate remains constant. Now, I ran out of room here, so I'm going to grab another sheet of paper, but the last thing that I want to go over here associated with the solubility at the particle level is this. It is the net effect of continuing solvation. And this occurs when the rate of solvation is greater than the crystallization rate. All right, so moving on here, we can talk about dynamic equilibrium and how it's related to our solution process. Now, our dynamic equilibrium is this. It is going to occur in the solvation process when the rate of solvation and the crystallization are equal. Now, when dynamic equilibrium is reached in the solvation process, no more solute appears to dissolve. In reality though, the solute particles continue to dissolve and crystallize. Now, during this dynamic equilibrium, the overall amount of dissolved solute is going to remain constant. Now, with dynamic equilibrium, the process is going to occur at constant temperatures and pressure. Now, let's talk about some terms here associated with this solvation rate here. And we get to our first two terms, and that is this. Number one, a saturated solution. And it's defined as a solution that contains the maximum amount of dissolved solute for a given amount of solvent at a specific temperature and pressure. Now, no more solute can be dissolved in a saturated solution. On the flip side here, an unsaturated solution is defined as a solution that contains less dissolved solute for a given temperature and pressure than a saturated solution. And what this means here with our definition of an unsaturated solution is that more solute can be dissolved in this type of solution. Now, our other term that we can associate here with solutions is that of a supersaturated solution. So a supersaturated solution is defined as a solution that contains more dissolved solute than a saturated solution at the same temperature. And you may be scratching your head and wondering, well, how is that possible? We just went over a saturated solution, and that's the maximum amount of solute that can be dissolved. Well, this process is going to occur when a saturated solution is formed at high temperatures and then allowed to slowly cool. Now, this is possible because some substances become more soluble with increased temperature, and this allows more solute to be dissolved. Now, supersaturated solutions are very unstable. Adding a small amount of solute or having a scratched or agitated container can cause a supersaturated solution to crystallize completely and very quickly. Now, some examples of where supersaturated solutions are used is in things like making rock candy or in a process called cloud seeding. Now, we need to talk about some factors that will affect solubility. So we start out with one of our two factors that affect solubility, and that is what temperature has on solubility. So again, this is one of the main factors that affects solubility. And so we can say this, that generally, as the temperature increases, the solubility of a substance also increases. Now, why do we generally see this trend, or why do we have this general trend? Well, number one, at higher temperatures, kinetic energy is increased. And so if we take a look at our graph here, you can see that most substances, as we increase the temperature, that solubility also increases. Now, what we have going here is a thing that we need to talk about with the temperature and that of a gas. So let's talk about the temperature and solubility of a gas. So for a gas, what happens is that as we increase temperature of a gas, the solubility is going to be lower. And again, we see that at higher temperatures, we have an increase of kinetic energy. And with an increase of kinetic energy, it's going to allow gases to escape from solutions more readily. So again, our general term here, our general association, is usually talking about that of liquid solutions. And we just need to clarify that because it's a little bit different that for a gas. Okay, so now we need to talk about one of our final terms here, and that is pressure and solubility. Again, this pressure and solubility here is another main factor affecting solubility of a particular substance. And so our trend with pressure and solubility is this. The solubility of a gas in any solvent increases as its external pressure is going to be increasing. Okay, so let's take this general trend into an example, and that's of carbonated beverages or a soda. So when a carbonated beverage or a soda is bottled, they are bottled at high temperatures. And again, I should have said carbonated beverages are bottled at high pressures. And what this causes is the carbon dioxide gas to be soluble in the solution. Now, when opened, the CO2 gas can escape from the solution. Now, the reason that the CO2 gas is escaping is because the pressure has decreased. Now, commonly, this is known as a flat soda or causes that soda to go flat. Now, the carbon dioxide is going to continue to escape from the solution until it becomes at equilibrium with that outside air. So again, it continues to escape until it becomes equilibrium with that pressure of that outside air. Now, what we can do with pressure and solubility is have another scientific law, and that scientific law is known as Henry's law. So Henry's law states that at a given temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas above the liquid. Now, with most laws that we have here in chemistry, there is a formula that is associated with this law. And so the formula is as follows. The solubility divided by the pressure is equal to that new solubility divided by that new pressure. So again, just breaking these variables down here, our S1 is our initial solubility, and that is in units of grams per liter. Your P1 is your initial pressure, and typically it's in units of atmospheres. However, sometimes they use a little bit different pressure, so I'm not going to specify the pressure. I'll make a note here at the end. But our S2 is our final solubility, again in grams per liter. And then our final term there is P2, which is our final pressure. And again, they typically use atmospheres, but there's no specified unit. I'll make a point here at the end. And so my point here with the pressures is this. No specified unit, but P1 and P2 must use the same unit for pressure. Okay, so let's go ahead and try Henry's law example as our last part of our notes for section 15.1. Okay, so here we go. It says if 0.85 grams of a gas at 4 atmospheres of pressure is dissolved in 1.0 liters of water at 25 degrees Celsius, how much will dissolve in 1 liter of water at 1 atmosphere of pressure, and we keep that 25 degrees Celsius. So again, our formula that we just got done going over is this. Our solubility, S1, our initial solubility divided by our initial pressure, is equal to our final solubility divided by our final pressure. So let's go ahead, let's just list out what we have and don't have. And so our S1 is equal to this. It is equal to your solubility, which is grams per liter. So check this out. We have 0.85 grams, but we need liters. So we're going to divide this by 1.0 liters. Okay, so it's grams per liters. Well, that's really easy math there. That's still 0.85 grams per liter. And then our first pressure here, it says that pressure is at 4 atmospheres. Now, no specified unit for pressure as long as P1 and P2 have that same unit. So we move down here to the solubility of our final end game here, and that's what we're trying to find. We're trying to find the solubility in 1 liter. So ultimately, this becomes our question mark, and then our pressure is decreased to 1 atmosphere. So the final pressure, P2, equals 1.0 atmosphere. From here, all we need to do is we just need to plug these numbers back into our formula, okay? So our S1 was 0.85 grams per liter, all divided by your pressure, which is 4.0 atmospheres. Now, this is equal to your final solubility divided by your final pressure, which was 1 atmosphere. All right, so now we need to use cross multiplication. We've seen this before. So what I'm going to do is I'm going to take 0.85 grams per liter times 1 atmosphere. So 0.85 grams per liter times 1 atmosphere is equal to S2 times our 4 atmospheres. So all I need to do to get S2 by itself is divide each side by 4 atmospheres. So what I'm going to do in my calculator is I'm going to take 0.85 times 1. And again, that needs to be in parentheses. So 0.85 times 1.0. Press enter. You divide that by 4.0 and you get a value here of 0.21. Yep, there it is, 0.21. Okay, so our S2 equals 0.21 grams per liter. And so ultimately here, 0.21 grams can dissolve. So I'm going to put a comma here, 0.21 grams are in 1 liter. Okay, so this would become our answer. All right, so I know this has been a lengthy episode. The big takeaways here are just become familiar with the definitions for solutions. Remember, there is a lot happening when a solution forms or doesn't form, and we can apply a lot of those terms. With Henry's law here, make sure you set up your equation correctly and you have the solubility in grams per liters. As always, I hope you have enjoyed this episode, and if you haven't done so already, make sure you subscribe.